All right, so number 7, it has 7 parts. It says the following data represents the speed at which a ball was hit in miles per hour and the distance in feet it traveled for a random sample of home runs in a Major League Baseball game in 2018. We're going to complete parts A through F. So first we want to find the least squares regression line, treating speed as the explanatory variable and distance as a response. So because of the number of data, like I said, I'm familiar with the calculator method, but it takes time. So I'm going to try to show you both StatCrunch and Excel on this one. So I'm going to pull up StatCrunch, and you'll be able to compare. And I'm going to pull up the information in Excel as well. So try to show you both of these methods at least once to help you kind of navigate those. Okay, so in StatCrunch, stat and then regression, I'm going to do simple linear. So we just got to pick the correct variables, which speed was the explanatory, distance was the response. So if you were doing like some extra testing, there's some other options, but for right now we're just going to compute the regression line. So pick those two variables, we're going to click compute, and we get the output table, which we've seen in the text if you look at the overview, and it kind of tells you a lot of information, but mainly you got the slope and the intercept. These are the first two values you see right next to their name. All right, so in Excel I'm going to do the same thing. What I'm going to do is I'm going to click and highlight the data. I'm going to go to insert, and I'm going to click this scatter plot diagram. Okay, so it'll do a scatter plot for me. Distance is the X, and can't really see how it labeled. It says distance in feet, but this is a scatter diagram. So once you get this to pull up, there's a little plus symbol here. So you can do a lot of different options and change the titles and things like that. Where did my options go? So I'm gonna come down here and click trend line. So trend line is going to give you like the line of best fit. It's showing you what that regression line would be. Click the arrow to the right, and we're going to click linear because that's the type of equation we want, and we're going to go down to more options. So these more options give you options to change the type of line you want. If you scroll down a little bit more, you have some other information that you can display. This one right here toward the bottom, it says display equation on the chart. So we're going to click that and then close this diagram. When you click that, it shows you the regression equation. Notice the similarity between the slope is exactly the same. So it's showing you that you're getting the same information from the StatCrunch. Look at the intercept, 84.268. 84.268, you're getting the exact same information. So you got two different methods that you can use. Again, I like to use a calculator, but just to save some time, because these are some tedious problems, you want to do it there to get you a little bit quicker. So now that we have our regression equation, we're going to do 3 decimal places, 3.114. And then the intercept was 84.268. All right, we're going to interpret the slope and y-intercept if appropriate. So remember, X was the, let me see, data, hit, squares regression. The speed was the explanatory variable, and the distance was response. So this is referring to speed, this is the distance. So the slope of the least squares regression line shows the distance the ball would travel when hit when the speed, what is this saying? The slope of the least squares regression line shows the distance that the ball would travel. No, The slope of the least squares regression line says the distance the ball travels increases by the slope with every 1 mile per hour increase the speed was hit. Yes. The slope shows the increase in the speed that the ball was hit for every 1 foot. Nope. Okay. So B is going to be our best interpretation of the slope. This one now says interpret the y-intercept. Y-intercept shows the speed. Nope. Y-intercept is the distance the ball would travel when the speed of that ball is 0. It wouldn't make sense to interpret that, because if the speed it was hit is 0, it wouldn't go anywhere. So in this case, it wouldn't make sense, I don't think, because if you put 0 here, that ball would not travel 84. So it wouldn't be appropriate in this scenario. C, predict the mean distance of home runs hit at 107 miles per hour. So look at our data. We do have that distance here, so it would make sense to predict that one. So let's do it. We don't have a 107, so we're going to predict that one. So I always try to look at what our data shows before we try to predict something that's outside the scope. So what I'm just going to do, I'm going to use the calculator. I'm going to use the equation that we have here. So I'm going to do turn it on, second quit. I'm going to type this equation in. I could do it on the graph. I'm just going to do it on the home screen. I'm going to type 3.114 parentheses. I'm going to put in the amount that we wanted to verify, which is 107, and then plus the intercept, 84,268. Okay, so this is the distance that we predict the ball would travel if the speed was 107 miles per hour. 417, we want to round to 1 decimal place, 417.5. All right, so if a ball was hit with a speed of 107 miles per hour, predict how far it will travel. If the ball was hit at a speed of 107, the distance that it most likely travel is. So this is the same thing. This is the mean distance, and then the distance that we think it would travel will be the same as the mean. We're just getting the average. So I'm kind of ask you the same question twice. Christian hit a home run, 398 feet. The speed at which the ball was hit was 106.2. Did this travel further than expected? So again, we'll do the same equation. We'll just plug in the speed of 106.2. So one neat thing about the calculator is I can hit second and enter. What it will do is recall the last equation. So I don't have to change everything. I can just come here and type my new value. So I'm going to type 106. Now, since there's an extra position, I want to do insert. It's in blue, INS. So I'm going to do second, insert, and I'm going to insert the 0.2 because I got those 2 additional data points. So then it shows the 106.2 in the middle. Hit enter, and we would expect that ball to go 414 or 415 when rounded to 1 decimal place. So the ball did not travel further than the predicted amount of 415. 415. All right, and then F, would you feel comfortable using the least squares regression models on home runs where the speed of the ball was 122 miles per hour? So again, if you look at your data, we're looking at the top speed, and from this chart, it looks like the top speed is about 110. So since 122 is outside of the scope of our data, it would not be wise to predict that because it gets more likely to have errors or further away from the average because we don't have data to model that situation. So it says no, least squares can only accurately predict the distance of home runs with lower speeds that were than what was observed, but not higher. No, that's not true. No, because the least squares regression model cannot predict the distance of home run when the speed of the ball is outside the scope. So this will be correct. So whether it was lower or higher, if it's outside the scope, we don't want to use it. So C is going to be the best response.